Let's work an example with constant acceleration in 2 dimensions. Here we're considering a skier moving with some acceleration of 2.1 meters per second squared down a slope of 15 degrees at some initial time. And what we want to know is what are the x and y components of the skier's position and velocity as functions of time, and what's her position and velocity at 10 seconds. So we have initial position and velocity given by these expressions here. These are not functions of time. These are just actual values. This is the position and the velocity. So first, I'm going to show you how to split up this acceleration into x and y components, and then we'll go on and do these parts A and B. So if we have my x and my y, we can write our acceleration. It's going downward down the slope, and we can split that up into an x component, ax, and a y component, ay. How do we relate those to our initial thing that we know, a? Well, a we know is 2.1 meters per second squared. And we also know the angle we're going down by. That angle theta is a 15-degree slope. And so we can say, since we know that angle we make with the x-axis, we can write our trigonometric relationship using this right triangle here to relate the hypotenuse of the triangle, that 2.1 meters per second squared, to the legs. Looking at one relationship, the cosine of that angle theta is going to be the adjacent side, so the side it's touching, ax, divided by the hypotenuse a. Because this is the angle with the x-axis, as long as we have the angle with the x-axis, this relationship will be true. We can rearrange this to solve for the thing we want to know, ax, by multiplying both sides by a, and plugging in our numbers, 2.1 meters per second squared and 15 degrees, we can evaluate this to be 2 meters per second squared is the x component of that acceleration. We can do the same thing for the y using the sine. So the sine is the opposite side over the hypotenuse, where this opposite side is ay. Again, as long as we know the angle with the x-axis, then this relationship will be true. If you have the angle with the y-axis, you can write the trigonometric relationship for that angle as well, or you can do a little bit of geometry to get the angle with the x-axis and then just always use these relationships. Whatever is less error-prone and makes the most sense to you. We can again solve this for the thing we want, the y component of the acceleration, and we get negative 0.54 meters per second squared. Lovely. Next, I'll point out, before going on, just a little aside, we can do what we just did, or if you want, you can treat this as a positive value. Even though our y is going down here, you can treat it as a positive and then use geometry to say, since my angle is going below the x-axis, that's a negative angle. Whichever way, again, makes the most sense to you. I'm doing it this way, where I'm plugging in the negative myself because I know I'm going down. But either way, you end up with the same result coming out of this. Now we're going to move on to solving parts A and B, and just note before moving on that we have x components here for our initial x position, x naught, and our initial x velocity, v naught, in the x direction, and for our y naught, and v naught in the y direction. So what are the x and y components of the skier's position and velocity as functions of time? We'll treat the constant acceleration in the x direction first, and write a constant acceleration expression that hopefully we'll be able to substitute things into to get a function of time. Using our initial values for x naught and v naught x, we can substitute those in, and that's an expression. Lovely. So we have position as a function of time. Notice the time dependence. How about velocity? Well, we can take that expression and we can take the derivative of it with respect to time. Derivative of 75 becomes 0. 4.1 times t becomes 4.1 of this over here, which was 1. I could have simplified this a little bit. 1 meters per second squared times t squared becomes 2 meters per second squared times t. Here, rather than keeping the units all afterwards, I've included the units on the individual constants in the expression. And then when you plug in a time in seconds, it should cancel out and leave you with meters per second there. So that's the x direction. We can continue on to do the same thing in the y direction. So constant acceleration in the y direction, we can use the same relationship. And now look at our initial y value and our initial velocity in the y. Substitute those in, and we have our y as a function of time. You can then take the time derivative again. Here, this will be negative 1.1 plus whatever this coefficient is times 2t. And indeed, that's what we get. Finally, what are the position and velocity at 10 seconds? To do this, we have a function of time. We can just evaluate that function, plugging in our 10 seconds, and we get a value of 216 meters. We can do the same thing for the y function, get negative 88 meters. And so our position as a vector can be expressed as the x component, 216, in the I hat, minus the y component, 88, in the j hat, with units of meters. How about velocity? Well, again, we have our velocity functions. We'll plug in 10 seconds to those, and we'll get values for the velocity in the x at 10 seconds, velocity in the y at 10 seconds. And then we can express our total velocity vector as the x component in the x direction minus the y component in the y direction with units of meters per second.